Howdy, this is your friendly neighborhood physics teacher here, and we are going to talk about Unit 2 FRQs on the AP Classroom. So it has two questions. We'll go over question 1 and then we'll jump over to question 2. So question 1 states, this question is a long free response question. Show your work for each part of the question. Then you see a little diagram. It's a table. Let's go ahead and draw it out. So it's a table with a box here, and it says 3. And we have a little pulley, string coming down, and ground, and then we have a box 1 and box 2 that's a little smaller, and it is more centered, but to give you a gist of what it looks like. So it says block 1 is resting on the floor with block 2 at rest on top of it. Block 3 at rest on a smooth table with negligible friction. So negligible friction means no friction, or not enough for it to affect it, is attached to block 2 by a string that passes over a pulley as shown above. The string and pulley have negligible mass, so we don't have to worry about, when we're doing our forces, we don't have to worry about the mass of the pulley and mass of the spring. Not string, not spring. And then for part AI, so it has two different, it has several parts there. So on part AI, on the dot that represents block 1, draw and label the forces, not components. So again, we don't have to worry about your X and Y components. We're just looking at forces exerted on block 1. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Draw the relative length of all arrows to represent the relative magnitude of the forces. So again, this is a true free body diagram. So direction and then length of the arrow matters. Your length represents your magnitude. So we're doing a free body diagram of block 1. So let's draw block 1. It does have a little dot, so everything's coming from the dot. So hopefully the first force you draw is force of gravity. You're like, yep, we have a force of gravity. And then block 1 is sitting on the ground, so we should have a force of normal. So we have ground, so we have forces, we have the earth pulling down on the block, we have the ground pushing back up on the block, but the block has another box on top of it. So we need to account for that force also. So we have another force going down. You can call this pretty much anything you would like. It's technically a normal force, but if you want to call it normal force 2, and then you could call this force a normal ground, G for ground. Anytime you do something weird like that, go ahead and do like right over here, equals force of normal from ground. So just label. You don't have to do anything. You could have just put an A there. You don't have to do anything special with labeling. You just have to make sure the graders know what's going on. And another thing is you want to make sure, so your force of gravity and your force of normal 2 should be, and this should be coming off the dot, so your blue arrow needs to be scooted over a little bit, but I want y'all to be able to see it. So they do expect you to kind of squeeze the two together. So let's see if I can go ahead and move that. So it is supposed to be coming off. So something like that. So your force of normal 2 and your force of gravity should be this added up should be the same as your force of normal G. And they're not going to sit, and they have, so if you see they have blocks already. So you could sit there and make 1, 2, 3, make your normal force 3 blocks, make force of gravity 2 blocks, and make your force of normal 1 block. So they can tell that 3, 1 plus 2 equals 3 type of situation. So it's a little bit more obvious. It's hard to do it this way because there's no grid on mine, but definitely use the grid. So that is A1 or AI. A double I says on the dot that represents block 2, draw and label the forces, not components, exerted on block 2. Each force must be represented by a distinct arrow drawn on and pointing away from the dot. Draw the relative links, all arrows to reflect the relative magnitude of the forces. Again, we're doing the exact same thing. We're just now doing it. So this was for number 1. Now we're doing it for block 2. And we did pink for block 2. So again, I hope the first force you go and draw is force of gravity. And then here we do have a force of normal going up. This force of normal going up is from block 1. And it says it's at rest. But it does have a string on it. But it says it's at rest. So this is where a lot of people get thrown off. People want to put a force of tension there, but everything's at rest. So hopefully you got that. Since everything's at rest, there actually isn't a force of tension. It's just chilling there. There just happens to be a string attached to it. So it's just your force of gravity and your force of normal. And again, you would want them to be equal. So if you made it 1 block, 1 block, or 2 blocks, 2 blocks, it doesn't really matter. You just want them to be balanced. And point-wise, if you're thinking point-wise, you got a point, you earned a point for labeling your arrows, and you got a point for the magnitudes being the same for part 1 AI, and the exact same thing, you got 2 points. So each of those were worth 2 points for labeling and magnitude. So let's check out part B. Part B states, block 1 is removed without disturbing block 2. So basically they take block 1 out of the scenario. So we're just going to erase, not the bottom of block 2, but so block 1 is taken out. Consider the scenario where the mass M3 of block 3 is greater than the mass of M2 block 2. Without using equations, make a claim about the motion of block 3 in terms of the balance or unbalanced forces. So you're not allowed to pull equations out. You just want conceptual. So they're not going to give you numbers. They're not going to let you use equations. That doesn't mean you can't sit there and write equations off to the side to help you think about what's happening. But they won't count it as any point. So this is BI. So a couple of things to think about. There is a net force on block 3, which is equal to the tension of the string. This net force will cause block 3 to accelerate to the right. So we're just looking at block 3. And the reason is, again, you can sit here and do a free body diagram. Let's do a free body diagram of block 3, which is orange. So the only force that's affecting it now is that force of tension, because it says there's no friction. So it doesn't matter that block 2 is less than block 3. It doesn't matter. That force of tension by block 2 is going to pull your block 3. Since that's the only force acting on it, it's an unbalanced force. If there's an unbalanced force, there's acceleration. So you could say something like that. Again, but I'm going to kind of do it like in little this because of this because of this kind of situation. Okay, so only force of tension is acting on it. Unbalanced force equals acceleration. So make that in a complete sense. RBII states derive an equation. Now we get to use an equation. Derive an equation for the acceleration of block 3 for any value of M3 or M2. Express your answer in terms of M3, M2, and physical constants as provided. So when we derive this equation, the only variables we can use is M3, M2, and any constants. That's probably the only really constant that would play a part is our acceleration due to gravity. Because there's no friction, we don't have a mu. So you got to think about, so we're dealing with forces. So we're going to start with F equals ma. And it's the sum of our forces equal ma. So what forces are kind of affecting our system here? And the cool thing, because of this string, so yes, this is in the x direction. Yes, this is in the y direction. The cool thing about the string, you can stretch it and think about it's going just like in a straight line. This is block 3. This is block 2. So we have a force of tension and the whole, so if we did here, so force of tension and force of gravity. So force of gravity is what's causing the whole entire motion. But we also have a force of tension this way. This is where Newton's third law comes into play. For every action, there's an equal and opposite reaction. So that's kind of like our whole entire system here. So what happens to our force of tensions? So if we were going to do our net force, remember net force is all the forces added together. So we have, and we're going to call, go back up. We're going to call this force of tension 3 and force of tension 2 because that's, so force of tension 3 is going to the right, so it's positive. Force of tension 2 is going to the left, so it's negative. In this case, gravity is going to the right, so it's positive. And that equals, now, because we're dealing with two objects, we have to deal with total mass, right? So our mass is both masses add together. So it's mass 3 plus mass 2 equals acceleration. You treat it as a system. Since it's moving as a system, it's moving together, you can treat it as a system. Since they're both moving, you need to take consideration of both masses. Well, since this is a positive and this is a negative, guess what? Your tensions cancel. So you're just left with your force of gravity equals m3 plus m2 times your acceleration. Since it's your force of gravity, guess what? That acceleration is just your acceleration due. Wait, no. No, it's not. My brain jumped. So acceleration. We know what our force of gravity is. This is where it comes in. So our force of gravity, now this force of gravity is with box 2, so that'd be mass 2 times our acceleration due to gravity. There we go. That's what I was trying to say. Hold on. And we're trying to solve for our acceleration. So let's go ahead and divide that real quick. So m3 plus m2. That cancels. So our acceleration is going to be m2g divided by m3 plus m2. There we go. So that's one way if you want to treat it. It's one big thing, you can break it down into, so there's a big or here, so you can do it that way, or you can treat it as two different sections. So we're going to take the sum of the forces of box 3 and sum of the forces, box is light pink, yep, okay, and sum of the forces of block 2. So block 3, we only have one force acting on it, which is force of tension. So it's mass 3A. Block 2 has force of tension going up minus force of gravity going down equals A. So the only thing that has in common is our A. Because that's kind of what, and so we're going to also tension of 3, tension of 2, force of gravity of 2. So there we go. We can actually break down our force of gravity here. So force of tension 2 minus m2g equals m2a. Remember, these force of tensions are the same. These force of tensions are the same. So we can just plug this into there. So we get m3a minus m2g equals m2a. We need to get like terms. We're solving for our a, so our a's need to get on the same side here. I'm going to go ahead and subtract our 3a on both sides. So we get a negative m2g equals m2a minus m3a. Pull out the a, and you get m2 minus m3, and that equals a negative m2g. Divide m2 minus 3m, m2 minus m3, and you get that a. And if you don't like that negative up there, you can flip some things around and get m2g equals m3 minus m2. So all I did is multiply everything by -1. So that becomes positive, that becomes negative, that becomes positive. And look, we got the same answer. Ba-dum-ba-dum. Oh, that should be a positive. There we go. So either way works. And for this one, you got a point for using Newton's second law, which is just F equals ma. So actually writing this down, you got a point for just writing that down. You earned a point for combining the equations, so doing it like that or doing it like that, you would get a point. And then you actually got a point for the correct answer this time. Amazingly enough. I know it's a rare thing to get points for correct answers. Part C says, describe in what way your answer to part BII is or is not consistent with your claim in BI. So this one's it's just a one pointer. You could just put it as a sentence, nothing too big. And yes, I said that block 3 would accelerate, and the equation in part BII shows that there is acceleration for any value of m3. So just saying yes, the equation and the free body diagram are the same. Woohoo! That's all you had to do. That was only 1 point. Part D says, on the axis below, sketch graphs of the velocity and the acceleration of block 2 after block 1 has been removed. Take the time to be 0 immediately after block 1 has been removed. So you had to sketch, so this is going back to 1D motion. So C was yes. D B, you had to draw, so we had to do a velocity graph, velocity versus time, and we have to do a acceleration graph. So basically, you have to remember, so it is going down, so you are going in a negative fashion. And it's a constant. Gravity's pulling it down. Now, it's going to be going a little bit slower than gravity because it's having to deal with, it's not in free fall, it's having to deal with two masses, but that should be a straight line. It doesn't look like a straight line. But it's a constant increase in velocity in a negative fashion. So remember, this is up here is positive direction, down here is negative direction, and remember our numbers. So that's 1, 2, 3, 4. This is -1, -2, -3, -4. The negative just means direction, so it just means it's increasing, just increasing going down. And then again, this is just saying it's a constant acceleration. It's constantly speeding up. It's just constantly speeding up in the negative fashion. That is question 1. Let's look at question 2. This question is a short free response question. Show your work for each part of the question. So we have a little figure here. We have two figures. We have one that has box A and a box B. And it says that right in the middle is our center of mass. And box A is going this way. Now, box A and box B have collided. Our center of mass is now right there. So they've hit, kaboom. So two identical boxes, box A and box B, are on a horizontal surface as shown above. There is negligible friction between the surface and the block, so we don't have to worry about friction, as shown in figure 1. Block A is initially moving towards block B with a speed of VA equals V naught. So it's just moving at some velocity. And block B is initially at rest, so block B is not moving. Figure 2 shows the blocks in contact as they collide a short time later. In both figures, the location of the center of mass of the two block system is indicated by an X that is labeled CM for center of mass. So part AI. On each of the dot, which represents the blocks where they are in contact during the collision, draw a simple arrow to indicate the direction of the net force, if any, exerted on each block. The net force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. If the net force is 0, for either, write 0 under the dot that represents the block. So again, they just have two dots. So this will represent block B, or A, sorry, this will represent block B, kind of going with the colors and the sides. And it's just, all you're doing is you're drawing which direction, so we're looking at as they collide, which direction the net force would be. So A would be pushing on B, so it'd be this way. And B would be pushing on A, so it'd be this way. And since they're the same mass, the arrows should be the same. They didn't give us a grid on this one, so just kind of eyeball it. So part 2. During the time that blocks are in contact, describe whether the center mass of the two block system is speeding up, slowing down, or staying the same. And then you select which one, and then you're supposed to give a brief explanation why. And let's see here, and even this one, you don't get any point for selecting the right one. You just get a point for explaining. but your center of mass's speed would end up staying the same. And so this was AI, this is a double I, so it'll end up staying the same. And a couple of reasons you could put, and this is only for 1 point, so you just have to put one reason. So a couple of reasons you could put is that the horizontal force on the two blocks are in Newton's third law pair and are initially internal in the system. So since block A and block B are it's the two block system, all the forces that are acting on it are in the system, and it's Newton's third law. You can say the net force on the two block system is 0, so that's why this force and this force should be balanced. There are no external horizontal forces acting on the two blocks. So that's another example of that. So you don't have to put all those, but any of those would have been good as an answer. So now for part B, it jumps to a different kind of figure. You are now at an incline, and it has block A moving down, and it has block B moving up. It still has the center of mass kind of in the middle, and it actually gives you the velocities. So it says this velocity is 0.35 meters per second, and this is the same, 0.35 meters per second. And the angle is 37 degrees. So for B, it states the surface is tilted at an angle of 37 degrees from the horizontal, as shown in the figure 3. The blocks are each given a push so that the instant shown they are moving towards each other. So BI states each block has a mass of 0.2 kilograms. Calculate the magnitude of the net force exerted on the two blocks at the instant shown above. It's actually asking for calculations. That's amazing. Okay, so it's wanting to know the net force of one block. It doesn't matter which one. It's just you pick one. So you get a point for providing either an indication that the forces for both blocks must be added together, or provide trigonometry relations to account for the angle of the ramp. So basically showing that, breaking down its X and Y components type of thing. And then you got a point is earned for providing a correct answer and showing the forces for both blocks are being added together. Okay, so let's just start with our net force equation. So net force equals mass times acceleration. So it's moving in the X direction. So we need to think about what forces are acting in the X direction. So honestly, the only force, this split second, because this is after someone has pushed it, in a split second, the only force that's acting it is the force of gravity in the X direction. So each one has a force of gravity, right? But we need to break down our force. Anytime it's tilted, we have to break down our force of gravity into an X and Y component. So we need the X component. So our force of gravity in the X equals our net force in the X equals our force of gravity in the X. And our force of gravity in the X, to do a little bit of trig here, that's a 90-degree angle. That's a 90-degree. That's a horrible 90-degree angle. Let's try that again, shall we? Ooh. That's a 90-degree angle there. So if this is our theta here, through the magic of it'd be the same angle down here. So then this is our hypotenuse. The force of gravity is our hypotenuse, so this becomes our opposite. This becomes our adjacent. So we need our x, so that's our opposite. So the sine theta is opposite over hypotenuse. For sine theta, our opposite is our force of gravity in the x. Our hypotenuse is force of gravity. So we get that our force of gravity in the x is force of gravity sine theta. Force of gravity sine theta. We can break down our force of gravity even more because we know that our force of gravity equals mass times acceleration due to gravity. And there we go. So now we just plug in what we got. It says the mass is 0.2. We know the acceleration due to gravity is 9.8. Sine, and our theta is 37. Make sure your calculator's in degrees. Once you plug that into your calculator, you get 1.2. And this is just for one block. We have 2 blocks. So we need to times this by 2. And you get 2.4 newtons for your net force of the 2-block system. And you need to show all of, you get a point for deriving, so you need to show all of that work. Now, that's a lot of work for 2 points, but you need to show all your work. For BII, it says, at the instant shown in figure 3, the blocks are moving towards each other at the same speed of 0.35 meters per second. Blocks collide at 0.5 seconds later. What is the speed of the 2-block system center of mass just before they collide? So we're looking for velocity. This is a 2-point question. So this was BI, so BII. So basically what you're looking for is, we're using our first equation, our final velocity equals our initial velocity plus AT. And we're trying to find our velocity. So we're trying to find our final velocity. Nope. We're trying to find our acceleration first. We have to find our we don't know time. So, I guess we do. It says it collides 0.5 seconds later. We do know time. There we go. So we need to find our acceleration. We need to figure out how it's accelerating. So our sorry, I'm looking at their key and their key isn't making sense to me. That's why I'm pausing. Because what their key has is delta V equals A delta T, which equals 6 times 0.5, which gives you 3. My question is, so that's our time. We're looking for our change, which is basically this equation. They just combined that. They just did your final minus initial equals T, and then that equals your change velocity. and they plugged in, sorry, wrong thing. They plugged in. So I understand where the equation comes from. I understand where the time comes from, because it gave us. But the acceleration at the instant. Oh, wait. Nope, we didn't solve for acceleration. We solved for the net force. We have the net force and we have the mass. So we can actually do F equals MA, our net force. So our net force is 2.4. Our mass would end up being, so we have to add the masses together. So 2.4 equals 0.2 plus 0.2A. So that gives you 0.4A equals 2.4. Divide. So you get 2. Hello, calculator. Let's work. Yeah. So 2.4 divided by gives you 6. There we go. They skipped a step. I was like, how in the world did they get 6? But my brain just had to. So you actually have to do this, and then you can plug in to get there. So you had to figure out your acceleration first. Since we had our net force, and we have our mass, and we had to double, because our system is both masses, we had to take both masses into consideration. So that is our acceleration. And then from there, we got our velocity. There we go. So that is unit 2 on our College Board classroom. If you have any questions, please let me know. Remember, you're loved and appreciated. Bye.